For this class of Data Communications and Network 1, it will be on Chapter 9, Routing, and it's lecture 18 of the video. Chapter 9 is, you talked about the routing decision in a packet switching network, okay? It depends on so how we make the routing decision and who makes the routing decision, okay? The answer is depend on the routing techniques, okay? We have the distributed routing, which is most common, and the centralized routing, okay, which is less common, okay? For the distributed routing, each node choose an output link, okay, for incoming packets. The distributed routing is common in this nowadays, okay, because the node is very smart, okay? The node is like computers, so it can make the decision, okay, by itself. But the centralized routing is kind of in the past, okay, when there is a destination or a designated node, okay, which is maybe network control center, okay, that make the decisions. So you have the only one node, okay, that is very smart, okay, which is kind of the main node that do make the decision for all the routing in the network. And the other node is just simple node, okay, that doesn't have to make any decision, just follow the order. This is not as robust as the distributed routing, okay, but it may be necessary if because of the cost, okay, of the node, okay, in the past. But the weak point is that if the network control center fails, okay, so the whole network will fail because there is no brain, okay, to make the decision anymore. The last one is called source routing. This is the case that the source station is the one who makes the decision, okay, and not the node, okay. In this case, maybe because of, you can think of it as like applications like taxi, okay. You take a taxi and you tell the taxi to go this way, okay, because you know that to go this way at this time of the day is the best, okay. So you tell the taxi that you should take the road and then take the highway, something like that. So this is source routing. But if you ask the taxi to make the decision, okay, you tell, okay, I don't know how to go there or which is the best way to go. So please take me to Gsetsat University, okay, from my home, for example. In this case, it is a distributed routing, okay, because the taxi is the one who makes the decision, okay. And sometimes, okay, you do the source routing because you have some special knowledge or special criteria, okay. For example, if you want to send sensitive for information for security, okay, then you may want to use some of the trusted link, okay, in the network. So you tell that you have to go only for this link, okay. You cannot go out of the military network, something like that, okay. So this is kind of rare, okay, compared to the distributed routing and the centralized routing. For the centralized routing and for the distributed routing. Now for the routing strategy, we have fixed routing, okay, such as the least cost routing algorithms that we talked about today for 2 techniques, and we have flooding, which we talked about, and we also have the random routing and adaptive routing, which will not be covered here. Okay. Now for the fixed routing, you always want to send or transmit with the lowest cost, okay, and the cost can be anything, okay, that is important to you. It can be the money or it can be the time, okay, to be that you want to minimize, okay. And the 2 least cost routing algorithms that we talked about today is the Dijkstra algorithm and the Bellman-Ford algorithm, okay. These are simple, but it's not flexible, okay. So it's not lack of the flexibility because the routes are fixed, okay. So there's no difference between routing of the datagram and the virtual circuit, because when you say, okay, go this way, will be visit this node and this node and this node will be the best, then every packet will follow this base route, okay. Whether it's a virtual circuit that you set up the connection first, or whether it's a datagram, okay, you always make decision to go this way, okay. So all packets of a source and destination pair follow the same route in this case. Now for the least cost routing algorithm, okay, so you will, in this algorithm, okay, you will base the routing decision on some form of least cost criteria. As I said, usually the least cost, the cost is the time, okay, to transmit, or the actual cost, okay, the money that you have to pay, okay. So then you will assign the cost, okay, based on some criteria. For example, if you think of it as application of on the road, okay, you're taking a car. If you go on the expressway, okay, that you have a tollway that you have to pay the toll or pay the money, okay, then it's faster, right? But you have to pay the money. So it depends on your criteria. If you want it to be cheapest to go, you may not get on the expressway. But if you want the fastest to go there, then you will take the expressway. Okay. So if you have to kind of transit, because in the network you have to transit many nodes, right? So this is, you can think of this as intersection, okay? So you may intersection on the street, okay? So you may kind of use the criteria as the number of hops, okay, to be minimized. For example, okay, go this way is the minimum number of intersection on the street when you drive a car, okay? So maybe you prefer this. So you can, the cost can be the number of hops, okay? So you minimize the number of hops that you have to, manual hop is like the node that you have to visit, okay? So if you have 3 nodes to visit in between, okay, so you have the, to go from one node to another node is like 1 hop, okay? Okay, and in this case, each of the link will have the same cost, okay, as 1 unit, but depend on the number of nodes that you have to go. So we can look at it this way. If you have a network, okay, and this is the node, okay. If you go this way, A to B, okay. If you go this way, you visit this one, okay, and then this one, and then this one. So you have 1 hop, 2 hop, okay. But if you go this way, 1, 2, 3, 4, okay, then you have 4 hops because you visit 1, 2, 3, 4 nodes, okay. The other part is 1, 2, and then arrive, okay, 1, 2, 3, and then arrive. So this one you have this one is better route in terms of hop, okay, fewer number of hop. Okay, so you can also minimize like that. Usually, if you have the higher link capacity, okay, for example, if the link is fiber optics, okay, so you have high link capacity, then you want people to use your link, right? Then you will cost for individual people, okay, you will cost individual user, you will cost less, you will charge less for them so that they will use your link, okay, so you kind of encourage people to use the high capacity link, okay. So the higher the link capacity, the lower the link cost is, okay. So you assign the cost to be low, okay, if it's like the fiber optics cable that you can allow many users to get into them, okay. However, if you have a lot of load on a certain link, okay, you can assign the link cost to be high, okay. For example, if you go to like on the street and there is a congestion, there may be an accident or a congestion, okay, at this junction, okay. For example, La Plau, okay, intersection is very congested, then you can put the link cost very high there, okay, because you want people to avoid going into that street. It's the same thing, okay. So if this link is not good, you put a high link cost on it, okay, and people will go route bypass go another way, okay, to reach the destination and avoid getting into that street or that link, okay. So that is if you do like adaptive routing, if you change the routing along the way. However, if you do the fixed routing, okay, you cannot adjust to the accident, okay, or the congestion in the network. So you just assign, okay, the cost based on what you can do best, okay, like maybe the time delay that you have experienced, or you have like statistic on it, okay, that in the morning should not go this way, something like that. Okay, for Dijkstra algorithm, okay, this is a least cost algorithm, okay, to this routing algorithm. In this case, you want to find the shortest path, okay, from a given source node to all other nodes by developing the path in order of, this is not if, okay, it's of increasing path length, okay. So you start with only one node, okay, and then you increase the path length, okay, include the second node and the third node and the fourth node, okay, until you cover all of the nodes inside of the network, okay. So step 1, you want to you just let T, okay, be a set of nodes incorporated so far. So at first, T is a set of nodes that is included in your search at this time, okay. As I say, at first it will have only the source node, and then you have increased one more and one more and one more until you include all of the nodes inside of the network, okay. So step 2, we initialize set T, okay, as to include only the source node, okay. And then you find the neighboring node, okay, that is not in T. So the neighboring node is the node that is next to connected to a source node, okay, that have the least cost path, okay, from node S, and then add it to the set T. We will look at it an example later that you understand better, but this is the idea, okay, the algorithm step. So then you add one more node, okay, to the set T, okay. Then step 4, you update the least cost path, okay. So you update the path, the cost for that part, okay. And then you repeat step 3 and 4. So now you have two nodes inside of the set T, right? Then you add the third node, another node, and then you add the fourth node and the fifth node. Every time that you add, you will update the least cost path, okay. So you add one more node, okay, until you all nodes are in the set T, okay. Now let's look at an example that if I have a packet switching network like this, okay, how do you find the route, okay, using Dijkstra algorithm, okay. You see that the number in the circle is a node, okay, node number, but the number on the line, okay, is the cost that you have to pay, okay, to use that link. And you see that there's arrow, okay, two-sided arrow. So node 1 to node 2 use one cost of 1 unit. Node 2 to node 1 also use a cost of 1 unit. So this is the same cost for both sides. Okay. In this case, the first step, okay, T equal to, if you want to source node to be node number 1, okay, and want to find the least cost path, okay, from the source node, node number 1. So at first you set T equal to only node number 1. So you include node number 1 inside of your set, okay. And then you find the neighboring node. So now it's node number 1. Then you find the neighboring node. Neighboring node, okay, you can look at it. Okay, you can. This is set T at first, okay, including only node 1. And then you look at the neighboring node, which is node 2, node 3, and node 6, which are connected directly to node number 1. Okay, so node number 2, okay, look at this. Node number 1 is connected directly to node number 2, 3, and 6, okay, but not directly to 4, 5, and 7. So you have only this 2, 4, 2, 3, and 6. Okay. And what is the value of the cost of the going from node 1 to node 2? Node 1 to node 2, the cost is 1. Okay. And node 1 to node 3, the cost is 3. Okay. And node 1 to node 6, the cost is 6. Okay. So this is what we have. And we will put it like this. The cost is the Dijkstra, okay, of node 2 equal to 1. So this is the cost from node 1 to node 2. Dijkstra sub 3 equal, d sub 3 equal to 3. The cost from node 1 to node 3, okay, equal to 3, something like this. Then you look at this, okay, you see that d sub 2 is 1, d sub 3 is 3, and d sub 6 is 6. So what is the lowest value, okay? The lowest cost is node number 2. So then you put node number 2 inside of the set, like this, okay? So you have node number 2 inside of the set. So the set includes node number 1 and node number 2. Now, you update the cost of the path cost, okay? So 1 to 2, you still have the link cost of 1, right? When you find the neighboring node of this set, okay, it can be connected directly to node number 1 or node number 2. So now you have an extra, two extra link, okay. So from 2 to 4 and 2 to 5, okay. So node number 4 and number 5, they are connected to node number 2, which is in the set that we have incorporated in the set T, okay? So we have these 4 links that we have to consider. If you go from 1 to 2 to 4, 1 to 2 has 1 unit, right? 2 to 4 has 4 units. So the total value is 5, okay? The cost is 5. And 1 to 2 is 1, 2 to 5 is 2, okay? So the total cost from 1 to 5, okay, via node 2 is 3, something like this, okay? So we have the d sub 5 equal to 3, d sub 4 equal to 5. d sub 6 and d sub 3 is the same as the last step, okay? Because they are still directly connected to node number 1. It doesn't change the path yet. However, you have to check, okay, whether if you go from 1 to 3 and 1 2 to 3, which one is cheaper? 1 to 3, use 3 units. 1 to 2 and 2 to 3, if you use 1 plus 3, okay, it will be 4 units. So this is higher cost. So you still keep the relative path from 1 to 3, which is 3 units. Again, 1 to 6, okay, there is no other path that can go from 1 to 6, okay, other than the direct path, okay, because now the set include only 1 and 2, okay, node 2 has no direct connection to node number 6, so you still keep it like this. So what is the lowest path, okay, of the neighbor, okay? You see that there is node number 3 and number 5 have the same cost, okay? You can include them at the same time, but I suggest that you do it one by one, okay, to not get confused, okay? So I will include in order, okay? So I will include node number 3 first, but you can also include node number 5, okay? Because it has the same cost, okay? But let's include node number 3. So when you include node number 3, okay, you have something like this. Okay, so I make it in the set consists of node number 1, 2, and 3. Okay, now I want to find the neighbor, okay, for this set. You can see that node number 7 is included now because node number 7 is connected to node number 3, so it's connected to the set. But before this, you cannot connect to node number 7, okay, from the node 1 and 2, okay, but you can connect from node 3. So you have the news route to node number 7. And also the node number 4, if you go from 1, 3, and 4, it is cheaper because the cost is 4 units, okay? because if you go there, go from 1, 2, and 4, the cost is 5 units. You go from 1, 3, and 4, the cost is 4 units. You can check from here. 1, 2, and 4. 1 plus 4 is 5 units. 1, 3, and 4. 3 plus 1 is 4 units. So you change the cost to go to 4, okay, by using the 1, 3, and 4. So you get this step, okay. Now what is the shortest, the lowest cost? Now it's D5, right? As D5, the shortest cost is the lowest cost. So you include now node number 5 in the set T. When you have node number 5, okay, now you can find, okay, the three nodes that are left, okay, 4, 6, and 7, that they are connected, all connected to 1, 2, 3, 5, okay. That is already in set T. You can see that the node number 7 is changed, okay. At first it goes from 1, 3, and 7. 1, 3, and 7 has the cost of 7, okay. But in this, when you update, okay, when you include node number 5, then you can go to 1, 2, 5, 7. 1 to 2 is 1 unit. 2 to 5 is 2 units, so it's 3. 5 to 7 is 1 unit, so it's 4. Okay. So now you have this new route. Okay. You have to check for all of the other nodes that is not included, but it is found that it's the same. Okay. So it's so node number 4 and node number 6, these are the best route already. Next, we have to include one more node, right? Node number 4 and node number 7, they are the same cost, so you can include either 4 or 7. But again, I will include in order. So I will include node number 4 first. So include node number 4. And find the neighboring node, okay, of node number 6 and 7 that is not included, that is connected to the with the least cost, okay, through the set, to the node in the set, okay. It's found that it's still the same path, okay. Next, I include node number 7. When I include node number 7 and I update it, I found that, oh, number 6 is changed, right? Because if I include node number 7, I go from 1 to 5, 7, 6 has a cost of 5, okay? But if I go from 1 to 6, has a cost of 6. So I change it to go with this part, 1, 2, 5, 7, okay, and then 6, okay? So this is the base part. That is the lowest to node number 6, okay? Then the next step, I have to include node number 6, right? So include node number 6, and I am finished with the routing algorithm, and this is the answer, okay? So 1 to 2 directly, 1 to 2 to 5, 1 to 3 directly, to 4 we will go 1, 3, 4, to 7 we will go 1, 2, 5, 7, to node 6 we will go 1, 2, 5, 7, 6. So if the mode 1 is a source node, this is the part that is like the best part that use the cost the lowest, okay, minimum cost to go to all of the nodes inside of the network, okay. So this is the Dijkstra algorithm. You can change and do it with source node number 2, number 3, number 4, number 5, number 6, number 7. Okay, you can change the source node, and you will get you may get different answer, and especially if the link, okay, the two directions are different. Okay, sometimes when you go one way, is cheaper than go another way. Okay, so it's so the path may be changed. Okay, and this is the next network that we'll see that going one way is one cost, going another way is another cost. Okay, different cost. But I will use this for Bell-Manford algorithm. Actually, this can also be used for the Dijkstra algorithm. Okay, if you know the structure of the network and the cost, you can always use fixed cost routing, both of the Dijkstra and the Bell-Manford. Okay. And in this case, the movement for is algorithm is to find the least cost path, okay, from a given source node, subject to the constraint, okay, that the path contain at most one link or one hop, and then repeat it, and then increase the constraint for include at most 2 links or 2 hops, and so on. Let's look at an example, okay. The first step, we will, okay, suppose node 1, okay, is the source node, okay, with 1 hop, okay, with 1 hop. Node 1 can go to node 2, 3, and 4, right? Node 1 go to node 3, 2, and 4, 2, 3, and 4. Node 1 go to node 2 with a cost of 2. Node 1 go to node 3 with a cost of 5. Node 1 go to node 4 with a cost of 1. So we have something like this. So the first step, you can see that you call, again, this is like the cost, okay? But you have the superscript 1, okay, on the cost, part cost. And superscript 1 is like, this is the constraint is like 1 hop, okay? So it's have a superscript of 1. So you can go to node 2, 3, and 4. Then for the next hop, okay, you allow 2, at most 2 hops, okay? No more than 2 hops, okay, to go from 1. So in this case, you can go to, with 2 hops, okay? 1 can go to 2, okay, only with 1 hop, okay? 1 can go to 3, 1 can go to 4. Now 1 can also go to 5, right? Because it can go 1, 4, 5. And 1 can go to 6 by using 1, 3, 6, okay? And then you can find the route. Also, if there are 2 routes, for example, 1 to go to 2, directly have a cost of 2, but 1 can also go to 3 and 2, or 1 can go to 4 and 2, okay? So you have to compare the values of each route and find the lowest values. Okay, so 1 go to 2 is still the best. 1 can go to 4 to 5. 1 can go to 3 by using 1, 4, and 3. 2 go to 6, okay? You can see that. Be careful of this, okay? If you go to 3, you will go 1, 4, 3. But if you go to 6, you will go 1, 3, 6, okay? You can see that this looks like that there is a loop, but this is because it's still in between the recursive, okay? When you repeat the step, this is not the answer of the final answer, okay? For the final answer, the route cannot have a loop, okay? If you look at the last example, you can see that. You can see that there is no loop, okay? To go to 3, it has to go this way. To go to 4, it has to go this way. There is no closed loop. If there is a closed loop, you will have a problem because you will not know which way to go, right? Suppose you have 1 go to 2, okay? And then suppose you have a closed loop like this, okay? This is a closed loop. You can see that if 1 wants to go to 3, okay? If it have something like this, just know that it have to go to 3 directly or it have to go like this, okay? So this is not acceptable. What is acceptable? It have to be something like this, okay? Something like this. It have to connect like this, okay? With no loop, okay? There must be no closed loop in the result, okay, of the routing to have no confusion. In this case, this is in between, okay, and you can see this is not really a closed loop, but because if it goes to 6, it will pass 3. But if it goes to 3, it will pass 1, 4, and 3. So you can notice that there is no arrowhead over here, okay? When you go to 3, there's no arrowhead. But when you go 4 to 3, this is the ending of the arrow is the destination, okay? Then you allow 3 hops, okay? For 3 hops, then you look at it again. You can arrive at everything, okay, at every node. For 3 hops, okay, what is the best to go to 2? Still 1, 2, right? What is the best to go to 3? Now it's best to go 1 to 4, 4 to 5, and 5 to 3, because the total cost will be 1 plus 1 plus 1 is only 3. But if you go directly, the cost is 5. Okay, so to go to 3, we'll go 1, 4, 5, 3, something like this. To go to 4, you go directly because the cost is 1. Go to 5, again, you go 1, 4, 5. To go to 6, okay, it's better to go past 4 and 5 because the total cost will be only 5. Okay, so this is your answer. Sorry, the cost will be only 4. Okay, this is your answer and this is the cost to go to each destination node. Okay, with source 1 as the node 1 as the source. Now, you have to keep doing this. Okay, you increase it to 4. Okay, and then you try to find the best route if you allow the hop to be at most 4 hops. It turned out that h equal to 4 have exactly the same answer, okay, as h equal to 3. Okay, so if you get the same answer, the algorithm will stop. Okay, so when you found that at this step, okay, when you increase the hop number is have the same answer as the previous hop number, then that is your final answer. Okay, the algorithm will stop at this step. Then you will you make the routing table. Okay, when you know. Okay, when you go to 2, you go to 2 directly. When you go to 5, you go to 4 first. Okay, and then to 5, something like this. So you have you can have the central routing directory. Okay, and you can have the node directory. Okay. The table inside of the node. In this case, node 1 want to go to 2, okay? It will go to 2, okay? 1 go to 2, it will go to 2 directly. If 1 want to go to 3, it will go to node 4. 1 want to go to 4, go to node 4. 1 want to go to 5, it's go to node 4. 1 want to go to 6, it's go to node 4. Know whether you can see this, but actually this is from node. Okay, this is 2 nodes. So source is node 1, you go to node 1, 2, you cannot go to node 1, right? 2, 3, 4, 5, 6. Okay, so inside if you go to node 2, 4, 5, 4, 4, 4, 4. Okay, so if you go to node 3, 4, 5, 6, you always go visit node 4. Okay, let's look at the diagram again. That's correct. If you want to go to 3, 4, 5, 6, you will go to node 4. Okay. The other's answer, okay, in the table, okay, we haven't shown you yet. I haven't shown you yet. You have to try doing it yourself using 2 as a source node, 3 as a source node, 4 as a source node, 5 as a source node, and 6 as a source node, and see what is the next node that it have to go, okay, in order to reach the final destination. Now, if you look at inside of the node 1 directory, you can copy the first column, okay? So you first copy the first column. So inside of node 1, you will have this table. Inside of node 1, you have this table that you want to go to node 2, go to node 2. You want to go to 3, 4, 5, 6, go to node 4, which is exactly the same as what you copy from the first column of the central routing table. This is the same as this. The same, okay? And the second, this one will be the same as for the node 2. Okay, and this one will be the same as node 3, node 4, node 5, and node 6 table. Okay, so you have centralized and you have the value for each of the node directory. Okay. So we are done with the fixed cost routing. Okay. Next, we will talk about the flooding algorithm. Okay. In this case, flooding is used. Okay, if you don't know anything about the network information. Okay. So for least cost routing, you have to know everything, right? You have to know how it's connected and the cost for each of the link. Okay. So you have to know the structure of the network and you have to know all the cost. Okay, then you can use least cost routing. But if you don't know anything about the network, okay, you cannot use that. Okay, then you can use flooding. Okay, so for the flooding, a packet is sent by a source node, okay, and will send to all of the neighboring node, okay, that is connected to the source node. Then when a node receives the packet, okay, it will retransmit the packet, okay, so it will make a copy, transmit to all of its neighbors, okay, except from the node that it has received from. And so one packet will be made copy, okay, many copy to go inside of the network. And so it seems like it will have, the number of packets will be increased more and more, right? And it may circle the network indefinitely. So in order to prevent this, okay, that will not generate too many and will not stay too long, okay, we can have the identification inside of the packet, okay, so that when this node receives the first packet, okay, and the second one, which is exactly the same as the first because it's a copy of the first one, it can know that this is the same, so it will not retransmit out again. It will retransmit only once, okay. So all duplicate packets can be deleted this way. Another technique is use hop count, okay. So you have to set a hop to a maximum values, okay, and then you reduce the number of the values of the hop count, okay, one by one. Every time that you finish a hop, so you go to this node, okay, the node -1, okay, hop count -1. Go to the next node -1 again. Go to the next node -1 again of the hop count until it reaches 0. Then the node will discard the packet, okay. So this is the two ways that you will keep control of the not too many packets. Okay. Now let's look at how a packet is transmitted, okay. For the first hop, if this is the network, okay, it's connected, but we don't know, transmitter doesn't know about this, okay, but this is the actual network, okay. So node 1 is the source, node 1 wants to send the packet, okay. So it sent 3 copies, okay, to all of the neighboring node 2, 3, and 4. Okay. Now node number 2 will receive the packet. Node number 3 receives the packet. Node number 4 receives the packet, right? When node number 2 receives the packet, it will make copies and send to neighboring node. What is the neighboring node of node number 2? Node number 3 and node number 4. So node number 2 will send to node number 3 and node number 4, right? Node number 3 receives the packet, and it's the same packet actually, but it's sent to all neighboring node, which is except the node that it has received from. So 3 will not send to 1. 2 will not send to 1 because it's just received from node 1, right? But 3 will send to 2, 4, 5, and 6, okay? Node number 4, again, make copies, send to the neighboring node. Node number 4 will send to node number 2, 3, and 5. It will not send to node number 1. You can see that only one packet now it generates a lot of copies already, right? The first hop, 3 copies. The second hop, 1, 2, 3, 4, 5, 6, 7, 8, 9. Another 9 copies. Okay, so already 12 copies of the same network. Now, okay, now you can see that node number 2 receive packet from node number 3 and node number 4, right? Receive from node number 3 and node number 4. Now, if it doesn't know that this is duplicate packet, if it doesn't use the identification, okay, and it's used like, for example, hop count, it will see the, let's say you set the hop to be equal, maximum hop to be hop equal to 3. So now it's the first time, okay, sent out. So when number 2 receives this packet, is like hop equal to 2, okay. When it receives the packet from another hop, okay, from 3, then it's the hop count equal to 1. So 2 receive packet from 3 and from 4, okay. So it make a copy. When it's received from 3, it will send to the copy that is received from 3. It will send to 1 and 4. The packet that is received from 4, it will send to 1 and 3, like this. Okay, so 1 will receive 2 copies of the packet, and 3 and 4 will receive another copy, because this is the copy that go to 4 is the copy that is received from 3. The copy that go to 3 is the copy that it has received from 4. Okay, so a lot of packet generated. Okay. Now, so number 4 received from 2 and 3. Okay. So it will send what received from 2, it will send to 1, 3, and 5. What received from 3, it will send to 1, 2, and 5. Okay. So we'll send 2 copies to 1 from 2 and 3, 2 copies to 5 again from 2 and 3, and 1 copy to 2 and 1 copy to 3 because it's received 1 copy. You know, it's like switch between them. Okay. Number 3 is the same. Okay. Number 3 received from 2 and 4. Okay. So when it's received from 2, it's sent to 1, 4, 5, 6. It received from 4, it's sent to 1, 2, 5, 6. Okay. So it generates a lot of copies like this. Okay. 5 is the same. Okay. Similar. Okay. 5 received from 3 and 4. So it will send from receive from 3 send to 4 and 6. Receive from 4 send to 3 and 6. Okay. At this point, this one hop equal to 3, right? The first hop equal to 3. Hop count equal to 3. The second one hop equal to 2. Okay, it's go to node number 2. Then it's hop minus 1. Okay, hop equal to 2. Then this one hop equal to 1. Okay. So when it's have received, okay, it will be discarded because hop equal to 0. When 2 sent to 4, this one, okay, the packet node number 4 will minus 1, okay, of the hop count. So the hop count will equal to 0. Okay. Now, suppose hop count equal to 3. Okay. When it's received, this one delete it. So the hop count equal to 2 for all of the packet going out. Then the packet going at this has the hop count equal to 1. Okay, has the hop count equal to 1. When all of the packet here have hop count equal to 1, for when it's received here, it will be hop count equal to this one minus 1, the hop count equal to 0. When it's equal to 0, it will not transmit again. So this is the last hop. Okay. Now you may ask, how can we know how many of hops, okay, to transmit, to set, okay? You kind of have to guess, okay, guess the number of links that you can reach out of the destination, okay, and set that as a number of hops. If you set it too high, okay, then you generate a lot of copies of the packet, okay? If you set it too low, it will not reach all of the destination. It may not reach your destination that you want because you don't know where your destination is connected to. Okay, now the property of the flooding algorithm is that it's very highly robust, okay, very, very robust. If there is at least one route that it exists between source and destination, okay, you can send the data to that destination, okay, because all routes between source and destination are tried. So it go to every route. So if there is only one route that works, okay, you can send it successfully. The application is for emergency message or military use. So if you want to send like maybe SOS, or you want to send like evacuation, okay, there's something wrong, there's some earthquake, or there's some flooding or something, and you don't know which network still work, okay? So you have to send the emergency message, like evacuate to this this direction, or go to this place, something like that. Okay. Then you have to you send to all of the network available, maybe all the mobile phone or television, radio, all of the possible way to reach as many people as possible. Okay. So this is what we do the flooding for. Also, when you try all of the hop, okay, it will contain a minimum hop route. Okay, so you can, since you try all of the hop, right, and if you set the number of hop count, and it will, if the destination receive, okay, the first packet that it received with the highest hop count left, okay, it means that this is the minimum hop count hop route. Okay, so if Like there is one, like number 5, okay, have received from 3 and from 4, okay. And if you look at, okay, what is the hop count of this packet, okay? The one that has the lowest hop count means that this is the shortest hop to go, okay? Which can be more than one, okay? So at least one copy will use the minimum hop route, and we can use the flooding to initialize at the initial state of the virtual circuit setup, okay? Because if you don't know what is the best hop route, the minimum hop, the route that visit the fewest number of nodes, okay? You can use this flooding, okay? And to check, okay, which is the lowest hop count. And so you use the flooding only the first time. And then after that, you can set up with the virtual circuit. Okay? And it's useful for the broadcasting if you want to, if not, maybe not emergency, but you want to broadcast to everyone, okay, then it's good to use this to have a high probability to reach the destination, okay. The disadvantage of the flooding is that it has the high traffic load, okay. So it's not practical in most applications. So we use it for special applications, okay. So that is for routing. So this is the end of the video tape. Thank you.